Friends, very good morning, good afternoon, good evening, wherever you are, and welcome to the Parallel Technical Session 1 in Hall A. It is my great pleasure to introduce the chairperson of this session, Mr. Ravikiran Vaidya, who is a principal engineer of geodynamics, and he has been very instrumental in popularizing the concept of deep foundation testing in India. And he has created a deep foundation testing industry. He has worked on several prestigious projects in the country and in several other countries as well. And he has several papers to his credit. He is the recipient of the prestigious Dinesh Mohan Award for Excellence in Professional Practice for the year 2018-19 by the Indian Geotechnical Society. And he is also the executive committee member of IGS, Deep Foundation Institute, and also on the Bureau of Indian Standards Committee, CED 40. And he has done his ME from MS University, Baroda in 1994. He is also a half marathon runner and national table tennis player in seniors category. Welcome, sir. And co-chair of the session, Dr. Amarnath Hegde. He is an assistant professor in the Department of Civil and Environmental Engineering at I.I.T. Patna. He obtained his PhD from Indian Institute of Science, Bengaluru, and MTech from I.I.T. Bombay. He has held the short-term research positions at University of Milan in Italy and UPC Barcelona Tech in Spain, as well as at NUS Singapore. Dr. Hegde published 2 books and more than 50 research papers in reputed international journals and conferences. He is a life member of several professional organizations like I.I.Sc, ISSMG, Indian Geotechnical Society, ISET, etc. And currently, he is the member of Technical Committee on Reinforced Field Structures, TC 218 of ISMG UK. He is also a member of Technical Committee on Geosynthetics of I.I.Sc Geo Institute. So it is my pleasure to welcome Dr. Hegde. So welcome Professor Dr. Ravikiran Vaidya as well as Professor Amarnath Hegde. Now I hand over the session to the chair as well as co-chair, please.
Thank you, Professor Srivalsam, and thanks for the introduction as well. I am happy that we have Professor Ayothiraman, who is well known in his field, for the keynote presentation. I take the opportunity to introduce him. He joined the Department of Civil Engineering in IIT Delhi in 2008, where he is currently working as a professor. And before that, he worked in IIT Guwahati as an assistant professor for 4 years. So he has about 20 years experience in teaching and research in the area of geotechnical engineering. Prior to that, he completed his graduation from Madurai Kamraj University in 1998 and post-graduation from College of Engineering Gindi in 2005. He completed his post-graduation with a gold medal. He has published about 90 papers in reputed journals and conferences. He supervised about 9 PhD theses, and about currently he is supervising 10 PhD research scholars. He has actively participated in various short courses, workshops, and national and international conferences, and also has delivered invited lectures in these forums. He is also a serving member of BIS for the National Building Code and the codes related to machine foundation. He has been a consultant providing technical advice to various metro projects like Delhi Metro, Kolkata Metro, Lucknow Metro, and other projects of national importance. So we would be very happy to hear you, sir, for the next 30 minutes. And we have a question answer session for the next 5 minutes. So those who are in the chat room or those who have joined online, you may kindly post your questions through the chat room, and we would take up them once the lecture is over. Welcome, Professor Ayothiraman, and the stage is yours.
Good morning to the chair and co-chair of the session, Dr. Ravikiran and Dr. Amarnath Hegde, and Dr. Srivalsa, the coordinator, and the delegates attending this conference. And in today's talk, I'll be talking about the tunnel foundation interaction in urban areas under earthquake load. And all of us know how this, urban transport, the metro rail projects have become a major urban transport mode actually. And this table shows, the kilometer length of urban metro rail projects all over the world actually. And you can see China is topping. And in India, currently the operational length is about 678 kilometers. And of course, with the ongoing construction plus proposed construction, it is going to be somewhere, 3,250 kilometers, which is almost second, right after China, once it's all completed actually. So this was in 2014. There were 22 cities, where metros were introduced. And we can see these red dots where actually the metros having underground construction. The yellow one are actually completely elevated actually. So there are many projects, where the underground tunnels are to be constructed. Of course, currently the government of India has actually proposed to construct in 31 cities, the metro project. So this is going to be one of the, lifeline of transportation in the country. This is the table summarizing, what is operational and then what are the under construction in several, metro cities, and the approved one and the proposed one. I think the government, even in the recent planning and the budget, you can see that, huge amount of fund has been, diverted for the metro construction. So these are in different cities, where the status of the work actually. And these are some of the cities for the first time they are going to be having a metro projects. So in Delhi, of course, very successfully it is functioning. 389 kilometers of, metro is functional, and then especially there are several lines where the underground, tunnels were constructed actually. So these metro transport can be elevated or underground. I think elevated is the very, convenient way of construction, cheaper, whereas underground construction is the most challenging. But it is unavoidable to have underground, metro construction, because you can see a very densely populated residential area. Obviously, you have to take this, metro underground and below these buildings actually. So obviously the challenge comes, how to ensure the safety of the existing buildings above this tunnel construction, and also the construction cost and time, increases significantly. But without options available, we are forced to go for underground construction as well in some areas of the, metro alignment. And this is, some of the metros where how much stretch of, construction underground kind of there are in construction. And the typical underground soil conditions, the tunnels have to be constructed either in soil and partly in soft rock condition as well. And of course, in Pune, it is also constructed in hard rock conditions. So eventually, we are talking about tunneling in soil as well as, rock conditions actually. This is some of the photographs taken, during the site visit in Delhi metro constructions. And you can see, the portal was there, and from portal, the tunnel construction is done through TBM actually. So this is the TBM components, the face of the TBM, and the complete, earth pressure balancing TBM is used. And the complete tunneling is, monitored by a computer control system. What is the volume loss, how much phase pressure has to be applied, and how much is the volume loss that is happening. As a result, the settlements are to be monitored at the surface, and the segmental linings are to be installed by the jacking. So this is how the soil, is collected through a mug and a conveyor belt, and the excavation is done actually. And we all know that these tunnels are, having a lining which are segmental, and these are finally, connected together and then installed by the jacking. So the major challenges that we have in urban areas, as we know that we are doing the tunneling underground, there are structures, above ground and the foundations. They come in the close vicinity, and then, so we need to take care of the safety of them actually. So there are two possible scenarios, we can look at it. One is during the tunneling, how much damage would happen to the surrounding buildings and the other subsurface structures, utilities. We need to protect them. But now you can see so much projects have already been, functional. The another possible scenario is these tunnels are existing, and these tunnel and metro alignments have become, obviously they become a major point of, attraction. So a lot of future development happens close to this metro alignment. So eventually any new construction activity also can actually cause, effect on the performance of the existing tunnel actually. So we need to also assess and, ensure the safety of the tunnels after construction also. So this is how you can see, the pile foundations are typically deep foundation, and the tunnels are also, varying from 10 to 30 meter depth. They will come in close contact. As a result, they may have interaction. And if these tunnels are located in a seismically active region, then their interaction under seismic load also need to be understood and then design accordingly. And nowadays buildings with basements are coming, so eventually they will also, come to relatively deeper depth. They can also have an interaction, with the existing tunnel. So we need to study the interaction of the shallow foundation also, and both under static as well as seismic loading. And all of us know in India, what is the significance of seismicity. And some of the cities where metro are already functional, they comes under from zone 2 to zone 4. Delhi comes in zone 4 with the zonal factor of 0.24. And what is the current state of practice with respect to tunnel design and the relevance? If you see, generally people assume that tunnel structure, underground structures are relatively, safe compared to the surface structures when they are subjected to earthquake load. But this has become kind of, question, because there are several case histories where the earthquakes have caused significant damage to the tunnels as well, underground tunnels as well, actually. So let us see some of the case studies, highlighted in the literature. And it is reported that these are the parameters that will affect the seismic response of the tunnels. One is the relative stiffness of the liner and the tunnel depth. Obviously, the peak ground motion parameters of the earthquake, and the duration and the predominant frequency of the earthquake. So those things will be the critical parameter affecting the performance and the damage of the earthquake tunnels. So there are 192 cases of tunnel failure were actually, kind of analyzed and reported, by several researchers, and we will see the summary of that. But typically, when to consider the seismic response of the tunnel, and we need to take into account into the design is whenever the tunnel depth is less than 50 meter, and typically in soft soils, and if your PGA is greater than 0.15 G or a magnitude is greater than 6, or your epicentral distance is about 50 kilometer, then we need to take into account the seismic design of tunnels actually, according to as follows. These are the case histories, which were analyzed and found out what will be the causes of the damage, whether it is effect of overburden depth, whether it is a effect of surrounding rock conditions, whether it is the magnitude of the earthquake, how it has caused the damage to the different number of tunnels, and what is the influence of the peak acceleration value on the damage, and similarly the epicentral distance. All these were actually categorically discussed by Sharma in June 1991. So it clearly shows that tunnels do undergo damage during earthquakes, so that we need to design them actually. I think there's many people, whoever talks on tunnel design under earthquake load, they will talk about this slide, how the deformation occurs in the tunnels depending on the incident of the wave direction actually. So it could be an axial, or it could be a longitudinal bending, or it could be a ovaling or racking deformation actually. So these things need to be taken and then designed. So this is what I would like to again summarize. What are the different possible interactions that can occur actually. Of course, when you construct a tunnel in soil, that soil tunnel interaction need to be understood even under static load. But metro tunnels are typically at close distance. They are twin tunnels, so therefore the tunnel interaction between the adjacent tunnel, second tunnel also need to be understood, because the in between soil, what we call pillar width, plays a critical role on affecting the the interaction between the tunnel as well. And of course, subsequently, the other two types of problem. Type 1 problem is where tunnel is constructed, then what is the response to the existing foundations? Then the type 2 problem, what we call is the tunnel is existing and there are some new construction activities, whether it could be an excavation or a foundation loading, and how they will affect the response of the existing tunnel. So, and of course, when they are seismically, active regions, so how the earthquake loading need to be considered. So today's presentation, I will mostly focus on the seismic design related issues, not the static interaction part. And most of the common methods that are adopted in the analysis of underground structures are, the quasi-static analysis, considering the free field method assumptions. There are also closed form solutions given by, Benzene and Wang, which can be used for a circular cross section of the tunnels. And of course, quasi-static analysis by racking method, considering the deformations can also be used. And obviously, we can do a numerical analysis, incorporating this quasi-static approach as well. And then a time history full dynamic analysis, can also be performed actually. So today we will be discussing about the case study of Delhi Metro, where, starting from a pseudo-static approach to quasi-static approach and then a full dynamic analysis. We'll be talking about, how different methods can give a different results and which one would be much appropriate to be used actually. So that's what we are going to discuss today. Of course, in tunnel design, one important factor which we need to understand is the flexibility ratio, because what is the relative stiffness of the tunnel lining and the surrounding soil. So that plays a kind of important role. And in fact, there is a reduction factor or a racking coefficient is applied when we do the analysis and design using the free field deformation approach. So this is the free field deformation, and the structural deformation to be applied for the racking analysis is by multiplying the racking coefficient, and this racking coefficient is function of the flexibility ratio actually. And another challenge is the segmental lining being used, so they do have a joints. What would be the effect of these segmental joints, because for a realistic analysis and design, one must model in the numerical analysis also the joint condition as it is, what is prevailing in the field condition actually. So Nagar has actually done an analysis and found out, that the joint stiffness do affect the moment and the thrust that are mobilized in the tunnel lining. So therefore, in our Delhi Metro analysis, we did consider the segmental joining modeling in the analysis. Also, we know that in soil engineering problems, so simplified elastic analysis or elastoplastic analysis, the soil constitutive model do affect finally the output of the moment and the thrust coming on the liner actually. So we do have to choose very judiciously the constitutive soil model depending on the actual soil condition, which is more representatively modeling the behavior. And some of the full dynamic analysis results reported in literature shows that as the PGA increases, you see that both thrust, axial thrust, as well as the bending moment on the lining increases actually. But again, these thrust and the bending moment need to be kind of reduced depending on the flexibility factor, because the flexibility is one of the important factors. So they can be reduced based on the flexibility value actually. So coming to the case study of Delhi Metro, this is a broad, flow chart giving the methodology how we have adopted actually. So we have to arrive at the input parameter. That's a big challenge, representing large number of borehole data. Finally, we have to come up with the input parameters. Again, Delhi having, certain part of Delhi having a shallow water table and a sandy soil condition in Yamuna River Basin, liquefiable. So we had to arrive at the different constitutive model for liquefiable soil condition and non-liquefiable soil conditions. And again, these parameters what you obtain has to be site specific. And again, for seismic loading, we have to also get the damping characteristics very representative actually. And of course, the challenges are how to arrive at the site specific ground motion characteristics, and how we are going to simulate the segmental joints in the modeling. And also you should be able to ensure the phase stability, which is actually kind of obtained in the TBM machine by applying appropriate phase pressure. So even numerically, you need to apply appropriate phase pressure value in order to simulate close to the field conditions actually. And the segmental linings are installed by jacking. Even that has to be numerically simulated, and how much jack force we should apply in the numerical analysis, that also is a big challenge. So these are the things we have actually simulated as close to the field condition as possible in our analysis and design. So of course, we have to arrive at these parameters, because most of the conventional geotechnical investigation report will have only SPT profile. And we did have a shear velocity profile for the Delhi region. So select location, but if not available, then we have used the correlation to convert from the SPT value to arrive at the shear velocity profile actually. So we have used the hardening soil model with small strain stiffness for Delhi soil conditions. And of course, the other dynamic characteristics were obtained from the Hanumantrao and Ramana equations, which are developed for Delhi region actually. And of course, the hysteretic behavior was assumed using the lower bound sand given by seed solution, and these are some of the properties used. So we have actually idealized the whole Delhi into three type of idealized soil profile for which we have carried out the analysis. And another thing is, instead of going for zonal factor for a time history analysis, you need to get the artificial, ground motion which are synthetically generated. So for that, we have used the target response vector method for actually, developing a synthetic ground motion for Delhi region. Again, we have used the NDMA guidelines which are given there, considering Bhavana and the Tigri fault, and we have developed the synthetic ground motion, time history of the ground motion actually. So which is for a particular target spectrum, we are able to closely match with, the ground motion giving the same response spectrum. And this synthetic ground motion was, eventually used in the time history analysis. And we can see that, how the phase pressure needs to be obtained for different cover depth, because as the cover depth increases, typically the phase pressure required to be applied increases. And when the phase pressure increases, obviously the phase displacement will reduce. The idea is you should apply a pressure which eventually will have a minimum phase displacement, so that that volume loss is also kind of, restricted to the limiting value, so that the surface structures are affected, not affected actually. And the jack force was also, applied in Delhi Metro, was quantified based on the recommendations of Bloom. And we also verified that the jack force, how much they are applying in the Delhi Metro conditions, which is almost 36 meganewton actually. And we initially started with the free field analysis, and in Delhi, the bedrock varies also from 10 to 80 meter, quite significant. Finally, we have gone for three different, bedrock that we have actually analyzed. And this is the shear stress variation with the depth for different, bedrock conditions. And again, for different ground profile that we have idealized based on large amount of geotechnical data actually. So we can see how the shear strain varies with the depth. And also we can see the acceleration, spectral acceleration at the surface, and the spectral acceleration not 7 meters below the surface. That's why, relatively the underground structures are actually experiencing a less spectral acceleration. That's why they normally assume to be safe actually. So we can see that for a Delhi region, whatever the spectral acceleration, the actual, acceleration based on the synthetic ground motor well within the design spectra. But this is for free field condition. The moment we bring in the tunnel and foundation system, they go in a totally different way. So initially a pseudostatic analysis were done as per IS 1890. And then we have also done some validation problem comparing the Wang solution and the Hassas solution. We can see that that liner thrust and the bending moment obtained were actually, comparable by Wang solution. So this shows that the numerical analysis is capable of capturing the tunnel lining behavior actually. And you can compare, the pseudostatic bending moment applied and the quasi-static analysis. We will always find that pseudostatic gives much higher bending moment. They always give a, very conservative forces actually. Of course, this red line shows, for the moment for which it is actually, designed based on the jack forces and other things, insulation forces. So that's why, the lining seems to be safe, because even though there is an increase in bending moment, but the handling stresses and the insulation forces actually govern the design actually. But there are other challenges, which need to be actually, cautiously, monitored, so which we'll be discussing in subsequent slides. And we can see that, how the thrust forces, using pseudostatic 2D and pseudostatic 3D, how they can vary. But the moment we go for the other approach, relatively less actually. And coming to the full dynamic analysis, we have to do the modeling as per, the conventional explicit, method of analysis, choosing the dimension of mesh, everything. And we can see that that increase in thrust, with time we are able to see, but all of them, there is not much increase in the, thrust force and the moment, considering the dynamic force. Even effect of joint stiffness also not significantly affecting your forces actually. So for a practical purpose, it says that, the joint stiffness condition can be neglected, for a quick analysis and design, for a practical purpose. And you can see that the increase in thrust is hardly 3 to 5% only. But of course, when you do the sequential tunneling, the variation for different two tunnels, they are not same actually. So they do have different forces, both moment as well as not exactly same actually. So you have to simulate the twin tunnel construction sequence in the modeling as well. And we can see that most of the time the increase in thrust and the bending moment, they are well within the design envelope. So this is the design envelope, positive bending moment for which we have to design. So the increase in forces are well within the design moment and the design thrust. So therefore nothing to worry about the design forces, but we need to worry something, the dynamic strain level that is built up on the lining due to earthquake forces predicted in full dynamic analysis, time history analysis. You can see that along the circumference of the lining, the two solid lines shows what is the strain limit specified by IS 456 for concrete, and you can see that certainly they are being exceeded. So the exceedance of strain level in the lining will eventually may lead to a crack in the tunnel lining, and these tunnels are underground and maybe below groundwater table. Slowly there will be a water ingress into the lining, and then they may deteriorate the reinforcement on the lining. There will be a long time deterioration of this tunnel lining, which is really need to be carefully monitored, and then appropriate remedial measure to be taken actually. So the major finding is that the strain level on the lining because of this need to be monitored. And this is clearly seen how the strain level for different cover depth. When it is shallow tunnel, the strain on the left and right tunnels are well within the limit of the concrete. And when it is relatively depth increases, they are comparable. And at some at a deeper depth, both left and right tunnel, the strains are much beyond the permissible limit specified by the IS code. So we have to be really watchful depending on the geometrical conditions where to put a monitoring of the strain level. And whenever the strain levels are alarming, what is the remedial measures to be taken? So we need to worry about it. And another thing is, we said that the accelerations are well within the IS code specified limit spectral acceleration, but under the presence of tunnel, there is a channelization of the seismic energy, and we find that the acceleration in the pillar width region has exceeded the IS code spectra. That means any structures located between the tunnel, they need to be designed for higher spectral acceleration. But if you follow IS code guideline, they may be in danger actually. So we have to be watchful when we design any structures between the tunnel in the pillar width region. And we then further went ahead to study the interaction of tunnel shallow foundation system. And we can see that different geometrical size of the foundation aspect ratio is simulated. And we can see that under the presence of tunnel, obviously tunnel being a stiff member, the load capacity increases. So there is an increase in bearing capacity. So as such, if you neglect the tunnel, your bearing capacity wise, we are conservative side. But if you want to economize the design, you can always, take care of the presence of tunnel and consider an increase in the bearing capacity also. But only thing, during the excavation, then there is a sudden drop in settlement. So when the tunnel excavation is happening, the settlement on the footing increases. But after the tunnel is constructed, then again, there is an increase in capacity compared to the load settlement behavior without tunnel actually. So that's what, we have to see. So during tunnel excavation, one has to be careful that settlements are not increasing. But if already tunnel is there, and if you are constructing a foundation, then we need not worry. The green line is, the post-tunnel construction, you are constructing the foundation, where you can see that, how the bearing capacity increases significantly compared to the no tunnel condition actually. So therefore, if you are, interested in taking the advantage of the tunnel, we can do that, but we have to kind of, come up with an estimation with proper numerical simulation actually. And again, as I mentioned, there is a bearing capacity increase, that function of depth of foundation as well as the geometry of the foundation. But by and large, 40 to 60% increase in bearing capacity could be there because of the presence of tunnel actually. And again, when it comes to dynamic load, we can see that that free field acceleration is somewhere here. But when the shallow foundation is there, in the vicinity of the tunnel, we see that the acceleration gets amplified actually, especially at a shallow tunnel condition. You see that the maximum acceleration is there actually. So we can see that. And again, similarly, we also did study the tunnel pile foundation interaction problem with no loading condition. That means only pile is there and the tunnel is there. And we also consider vertical load on the pile. We did consider lateral loading on the pile and also pile group configurations actually. So different scenarios of field conditions were modeled. And in this case, we have assumed 1 meter diameter pile, which is most commonly used these days actually, and for which the vertical settlement of permissible settlement of 12 mm is used and a lateral deflection of 10 mm is used actually. We had only modeled the pile up to the invert of the tunnel, because beyond which the load distribution goes much below the tunnel, so the interaction may not be significant actually. And also seismic loading also for pile group, the permissible settlement of 25 mm as per IS code was used. And we did also a validation problem by comparing law of fields data reported on the pile behavior. And then it is found that there is a large, displacement around the pile and the tunnel, for a distance, and they are actually, typically well within the 45-degree line from the springing line actually. So you can see we have plotted a normalized pile settlement curve with the distance from the pile actually, tunnel, and distance between the tunnel and pile. And we can see that when the distance is small, then the deflection starts increasing, and then they reach the full settlement value actually. So similarly, for a loaded condition also, they actually reach the maximum settlement. So the critical distance, for a different cover depth were established actually. So obviously for a shallow depth, that actually they reach the maximum settlement at a very close distance. At a deeper depth, because of confinement, you see that maximum settlement is reached, relatively at a long distance between the pile and tunnel actually. Even the dynamic analysis indicates that there is a settlement obviously is less because of the stiffening effect provided by the tunnel. And also when the pile group width increases, the settlement actually decreases. That group spectra again, is totally different from the free field spectra because of the presence of, your stiff elements, that is both pile as well as the tunnel. They have a different relative stiffness. As a result, the free field response spectrum is totally affected. You can see this is the free field, and this is under the presence of, your tunnel and pile. So the frequency content and everything gets shifted. You can clearly see that actually. Seismic settlement seems to be less, so only 3-4 mm, that can be neglected. And again, the same channelization effect is happening. The acceleration, spectral acceleration in the pillar width area is increasing. So as a result, the forces, although settlement is less, the forces coming on the tunnel, the pile, on the pile group, they are increased actually. So therefore, we need to check the pile design for these additional, inertial forces that are coming in a pillar width area actually. So that one has to check actually. To summarize, we may use pseudostatic methods, which are most commonly used in industry, which may be giving in conservative in giving the liner and the liner forces, basically thrust and moments. But the challenge is it cannot give the time variation of these forces, and especially the strain and displacement, other things cannot be predicted by this method. So therefore, although it is conservative, but with respect to deformation and strain, it doesn't give any information. We may use the closed form solution as well for a typical cross section of circular tunnels by Wang, but Wang method seems to give a better solution compared to Benzene method. So for ideal cross sections, we may use the Wang solution as well actually. Of course, the full dynamic analysis is always, more rigorous, and it can simulate the realistic conditions, all the construction sequences. But again, your results, accuracy is function of how accurately you are modeling the site-specific ground motions, and what is the appropriate constitutive model that you adopted, and also how accurately you have simulated the construction stages. So accordingly, your results will be varying. But the most critical output that we have come out is the dynamic strain is actually increasing for a certain geometrical conditions and loading condition, which is really alarming. You need to monitor the critical sections identified, and finally, whenever the strains are increasing, then we may need to go for appropriate remedial measures to be adopted actually. So with this, I thank the organizers for giving me this opportunity to interact with the delegates who are attending this conference, and I would be happy to discuss if there are some queries. Thank you.
Thank you, Professor Ayothiraman. Excellent presentation, I must say, and very lucid. We have a few questions. Are you able to see those questions, or should I read it out for you?
I am able to see that. So, yeah.
Great.
So, thank you very much for this huge amount of. My question is, could we consider radial or horseshoe-shaped tunnels more efficient to resist earthquake loads compared to other cross sections? Actually, so as I have mentioned, see, we have the earthquake-induced forces are actually, coming. The increase in thrust and moments are kind of nominal only. Of course, it depends on the flexibility. For a Delhi region, if you see the Delhi soil conditions are relatively, dense and stiff. If you see the Delhi, especially where the underground metro tunnels there. So the n value is slightly large actually. So therefore, in this case, we have found out to be marginally less, but there can be increase in force as well, as we have seen in some of the cases. But the question is, the still the installation forces like jack forces and the other handling forces, they are already, governing actually the, design forces. So therefore, I don't think the shape of the tunnel would be a significant thing in terms of the design forces. But of course, as I mentioned, the strain level would be totally different. Right now, we have done for a circular tunnel. If you come up with the horseshoe or other shape of tunnel, the strain developed on the lining would be different, which we need to study actually. And the second question is, have you come across any case in India where TBM had to, TBM had to go through an existing pile foundation supporting a building? And how did you tackle the load flow? Yeah, I think there are several cases, where the not only the pile foundation, even there are heritage structures, which has come across, on the alignment of the TBM tunneling, and they have been monitored. So the extensive monitoring is done, for those pile foundation supported structures on the heritage structures as well. And then whenever there is an alarming, then appropriate remedial measures were adopted. Actually, there are a lot of examples. Yes.
Yeah, one more question from mine, because there have been several low intensity earthquakes since 1998. That's when the first Delhi Metro was planned. And obviously, you would have had some PGA acceleration measurements and other instrumentation which would have measured these low intensity earthquakes. And was there like an effort to match those field findings with the constitutive modeling and trying to extrapolate or generate the responses so you are more on the right curve? I mean, is that a continuous effort? How is that like?
Yeah, we are working with DMRC also. We are trying to collect this field monitoring data of these, buildings for which the deformations are monitored. And we do have the earthquake data for the, the earthquake that have happened. But only thing, the design spectra is for a magnitude of 7.
Correct.
So so if you see these magnitudes are relatively low, whatever these earthquakes have happened actually.
Yes, they are much lower. They're much lower.
Much lower. So therefore, the exact correlations, because this monitoring, especially during tunneling, was done. So as such, the continuous monitoring is actually in the pipeline. The problem that we are talking about, monitoring of the strain at the critical cross section, that is not being implemented. So whereas so this is the proposal, we are working with them. And once this data continuous monitoring is available, what you are suggesting is that that's a very good suggestion. We can really, come up with, even for those lowest magnitude, we can do back analysis and do some.
Correct, because then you can refine the model. I think that is something I thought that was being done, but okay, I understood. Okay, great.
That's a very good suggestion, sir. Yeah. That we can. Yes.
Okay. Sure. So with this, thank you, sir. Thank you once again for the presentation. I request Dr. Amarnath Hegde to take over from here for the rest of the presentations.
Yeah. Thank you, sir. Thank you, everyone. Thank you, Chair, and thank you, Co-Chair. Thank you,
sir. Yeah. So thank you, sir. So it's my basically pleasure and honor to basically take forward the second half of this session. So in these sessions, we have 4 technical presentations, and as per the conference guidelines, 10 minutes is allocated for each of the presentation, and out of which 8 minutes for presentation and 2 minutes for Q&A. So what I do is that around 7 minutes, I will give a gentle reminder to the speaker so that he can plan to finish his presentation in next 1 or 2 minutes. And I also request audience to take part actively and post their question in the chat bot. So at the end, I will take up the question and convey it to the presenter. So with this brief, now I invite Dr. Arup Bhattacharya of Jorhat Engineering College, Assam, to present his paper on comparison of response of pushover analysis and dynamic analysis of pile foundation. Dr. Arup?
Yes, I'm present. Hello, can you hear me?
Yes, we can hear you. You can share your screen, sir.
Yeah. Good afternoon, everybody. Here I'm going to present a comparison of the response of the pushover analysis and dynamic analysis of the pile foundation. Now, we know that the prediction of the foundation ground system, the seismic loading, is very challenging, and because it depends on the soil foundation interface mechanism as well as the nonlinear soil behaviors, which considering the soil structure interaction in the model. Now, the dynamic analysis in the conventional seismic method, finding the response of the structure is by conducting the dynamic analysis, we can find out what is the response of the structure. But in recent times, the pushover analysis, nonlinear pushover analysis, also used to determine whatever the peak load acting on the structure and what is the response of the structure. So based on that one, some literatures based on the pushover analysis. In that one, by the Mukhopadhyay et al. 2008, they have conducted on the stratified soil. They found out what is the response of the pile soil interaction, and they found that they determined the load displacement curve from that one, and they found that the load displacement is affected by the types of the soil. And then soon et al. Conducted compared some pushover analysis and the dynamic analysis, and they found that these are almost put a very good pushover analysis gives a very good response of the dynamic analysis. That whatever the response we obtain in the dynamic analysis, the pushover analysis also gives the almost similar type of the response. So based on that one, we can summarize that the numerical fundamental FE analysis can be used to find out the what is the soil structure interaction mechanism. Then by using the OPENSEES PL also we can determine that one, and the nonlinear pushover static pushover analysis can be used to simulate the seismic design for the pile formation, and the pushover analysis is static inelastic nonlinear seismic analysis, which can be give the characteristics of the behavior of the pile formation. So based on that one, the objective of our study is to the dynamic analysis as well as the pushover analysis of the pile surrounded by the different types of the soil layers, and to check the accuracy of the response of the whatever we obtain from the pushover analysis and with the dynamic analysis. Now in that one, we have considered the soil pile interaction, and given in the Lu et al. 2011 and the Wang et al. 2015, and these are the model parameters considered by the Lu et al. And based on that one, we have these are the model numerical parameters used for the simulation purpose, and we have obtained these are the results, validation results in the OPENSEES PL. In that one, we found that the results obtained from our analysis and the results obtained given by the Lu et al. And as well as Lu et al. Is almost similar for the pile deflection as well as the bending moment profile of the pile. And then we have compared that one with the nonlinear and the linear analysis by conducting the nonlinear and the linear analysis in the OPENSEES PL. And we have compared that one with the results obtained from the Wang 2015. And we found that our results are with very good accuracy. Then we have modeled the different types of pile and the soil, the different types of soil. So we have considered the 10-meter long pile having a diameter of 0.4 meter and and the 0.8 meter, and it is fixed at the top and the bottom. And for modeling of the pile, we have used the beam column, linear beam column element, and for the interface, these the links are used to model this interface between the soil and the pile and the surrounding soil. And in case of the soil, we have used the 10-meter soil domain, and it is modeled as the 8-meter brick element with the multi-material, and the different types of the cohesionless and the cohesive soil are taken into consideration for this one. Now, these are the different soil pile interactions. That means the different soil layers considered for the finding out the soil pile interaction. So there are two layers. There are two layer system. One in that one there is one layer 1 and the layer 2, and there are also 3-layer system. In the case of the 3-layer system, the thickness of the top layer is considered as the 2 meter, and the thickness of the middle layer is considered as the 6 meter, and in case of the thickness of the bottom layer is considered as the third layer is considered as the 2 meter. And these are the different combinations of the soil combinations surrounding the pile by considering the layer 1 and the layer 2, cohesionless dense sand, cohesionless cohesive medium soil, and the cohesionless loose sand. We have considered the different types of the soil and based on soil. So these are the their combinations, whatever we have considered for our study. And this is we have conducted the dynamic analysis by applying the peak ground acceleration of 0.3 g, the frequency 2 Hz in the longitudinal direction, and we have considered the 10 numbers of the cycles for the this one, so which represents almost the magnitude of this Richter 7 as per the seed and at least 1970. Now, these are the pile head displacement obtained for the different types of the soil, having the for the different diameter, pile diameter 0.4 meter and the 0.8 meter, and these are the pile head displacement obtained from the dynamic analysis. And then we try to determine the bending moment also along the depth of the pile. So these are the bending moment profiles for the different types of the soil. This is for the pile diameter of the 0.4 meter. This is for the 0.8 meter, 2 layers, 0.4 meter pile diameter, and the 2 numbers of the layers. And this is 0.4 meter diameter with the 3 numbers of the layers. Here it is 0.8 meter diameter for the 2 numbers of the soil layer, and the 0.8 meter diameter for the 3 numbers of the soil layers, and these are the bending moment profile we obtained. Then we have conducted the pushover analysis. In the pushover analysis, we have applied the horizontal monotonic incremental loading till the pile head displacement become equal to the whatever the pile head displacement obtained in case of the dynamic analysis. And these are the bending moment profile of the pushover analysis. The first one is for the 0.4 meter diameter with the 2 numbers of the soil layer, and it is 0.4 meter diameter with the 3 numbers of the soil layer, 0.8 meter diameter with the 2 numbers of the soil layer, and the 8 meter diameter with the 3 numbers of the soil layers. And now then we have compared the maximum bending moment witnessed by the pile during the dynamic analysis and the pushover analysis, and we have found for the different types of the soil. So this is the first one for the first one is for the cohesionless dense sand with the 0.4 meter diameter, and we found that this is the maximum bending moment in case of the pushover analysis around 1200 kilonewton meter, and in case of the dynamic analysis, we have obtained this one as around 1100 kilonewton meter. So in this way, for the different types of the soil, different soil combinations, we have obtained the maximum bending moment obtained from the dynamic analysis, and the maximum bending moment obtained from the pushover analysis. And we have found that here with the change in the soil combination and the soil type, the amount of the maximum bending moment generated in the pile varies in case of dynamic as well as in case of the pushover analysis. So these are also the different types of the for 3 layers of the soil. For the 3 layers of the soil, the maximum bending moment generated in the dynamic analysis and the pushover analysis. And from all these analyses, we have found that the maximum bending moment is affected by the layer combinations as well as it is affected by the soil type. That means that if there is a loose sand, then the maximum bending moment will be different. If it is a dense sand, then it will be different. And then also we have found that the pushover analysis can predict whatever the response obtained in the dynamic analysis. Pushover analysis of the pile can predict almost similar type of the response that can be obtained from the dynamic analysis. Then we have
I request you to conclude in 1 minute.
Yeah.
Thank
So
you.
here, then after that one, we have drawn the moment curvature relationship for the different types of the soil, and for every depth we have determined, and from that one we try to find calculate the yield moment of the pile embedded in the different types of the soil. That means these are the yield moment obtained for the 2-layer soil, and from that one we try to find out the location of the yielding zone where there will be maximum yield moment. So based on that one, for different soil combinations, so we try to locate the yielding zone, and this is for the 2 different types of soil layer. These are the combinations given here. So these are we have obtained that it varies between the 3.3 meter to the 6.67 meter. That means yielding maximum yielding will occur within this range. And then for the this 0.8 meter diameter soil with the 3-layer different types of the layer, we have conducted determined the yield moment, and from that one we try to locate the yielding zone, and we have found that the this type of the soil, that is for cohesive steep soil and the cohesionless dense and the cohesive steep soil, the yield moment will vary in between. The yield moment will be in between the zone of the 2 to 4 meter, and for other type of the soil, it will the maximum yield moment will occur within the zone of the 2 to 6 meter. So based on that one, we can conclude that the pushover analysis and the dynamic analysis can be the pushover analysis can be used to determine the predict the response of whatever we obtain in the dynamic analysis, and based on the pushover analysis we can determine the yield moment and the yield zone, and from that one we can this yield moment and the amount of the yield moment and the amount of the yield zone is affected by the surrounding soil type. Thank you, sir.
Thank you for excellent presentation. There is one question by Mr. Sheikh. So what he's asking is, what is the fundamental difference between pushover analysis and dynamic analysis?
So dynamic analysis is the time history analysis, whatever we conduct in the time by applying the actual ground acceleration, the ground acceleration history, we conduct the dynamic analysis. And in case of the pushover analysis, what we do, we apply a static force at the top, and we try to see the response, this means we have to apply the static force up to the displacement, whatever we displacement obtained in case of the dynamic analysis. That means the static force is applied at the top, and the displacement, whatever the displacement of the pushover, the maximum displacement of that will be equal to the maximum displacement whatever we obtain from the dynamic analysis. So in that way, by conducting the pushover analysis, we can find out some response of the dynamic analysis. We can visualize the response of the dynamic analysis. So it will be a slightly easier way, lesser time consuming, and whatever the computing system required also much lesser in case of the pushover analysis than that of the dynamic analysis.
Yeah, thank you. So there are no more questions. So then I will thank Dr. Bhattacharya for excellent presentation. So now I invite Dr. Ketan Bajaj of Swissray Delhi or his team, elastic seismic design response spectra for deep and shallow basin of the Indian subcontinent. So Dr. Ketan, I could not find him. Any co-author here?
I think he is not there. We can move to the next one.
Yeah. So
if he joins later, we can see.
Yeah. So then we'll move to seismic effect of underground box structure by metro and subways with varying soil parameters by Chiranjeev Sarkar of ACOM Delhi. Chiranjeev?
Yeah, am I audible, sir?
Yes, you're audible. You can share your screen.
Okay, sir. Okay. So, good afternoon, everyone. Introducing myself, Chiranjeev Sarkar, a senior structural engineer from ACOM India Private Limited. Today, I am going to present my lecture on seismic effect of underground box structure for metros, subway with varying soil parameters. So these are the overview of my presentation: introduction, methodology, model of the study, result and discussion, conclusion, and references. Introduction. Nowadays, tunneling and underground structure are playing a very vital role in improving space congestion problem as well as the sustainable development of the concerned location. So many cities are having plan or to construct underground structure for metros and subways. So this structure may undergo severe damages caused by excessive deformation due to the seismic shaking. Hence, it is necessary to have an accurate estimation of deformation and bending moment caused by the movement of the surrounding soil under seismic condition. Actually, seismic design of underground structure has not yet received adequate attention in the past days. Actually, they usually suffer lesser damages in comparison to the above structure. This was the reason. However, Dakai underground substructure in the Kobe earthquake collapse in 1995. This event was reported the first modern underground structure failure during the seismic loading. Later on, there are many more instances of severe damages. So among of them, few significant of them are Loma Porte earthquake 1989, then Kobe earthquake 1995, Sichi earthquake 1999, then Tohoku earthquake 2011. So it is very important to examine the performance of the underground structure against the natural hazards like earthquake because of their importance for saving life and economy. So in my present study, an attempt has been made to carry out a parametric study of a typical cut and cover box structure of 9.6 meter wide and 5.8 meter height, situated at varying ground condition like loose to medium sand, medium to dense sand, and very dense sand at different seismic condition, that is seismic zone 3, 4, etc. So outcome of the each and every cases has been tabulated and reported for further analysis, and so that we can come out some correlation and some conclusions. So methodology. Seismic behavior of box structure basically adopt free field deformation or racking analysis. The term free field deformation basically defines the ground strain produced by seismic wave in the absence of excavations. Racking deformation of rectangular tunnel is generated basically due to the shear distortion during the earthquake. Seismic effect of underground structure is basically determined from the racking force, which is basically required to generate the estimated deflection with respect to the surrounding ground strain. So the maximum ground strain we can see from the equation, that is nothing but a basically ratio of peak ground velocity by shear wave velocity. So model of the study. A typical Delhi Metro box cut and cover tunnel structure at Dwarka-Najafgarh corridor has been considered in the present study. So this section is basically situated at Delhi Najafgarh area, which is already constructed during the phase 3 work of the DMRC. You can see the typical cut and cover tunnel cross section here. So cut and cover method of construction has been adopted during the construction with the help of the diaphragm wall, which is basically part of the earth retaining structure as well as the main body structure. So ground condition till up to the depth of the tunneling was mostly varied from the loose silty sand to the medium dense sand at different stage of the tunnel of the alignment. Also, Delhi lies in the seismic zone 4. On the other hand, similar type of section at Lucknow Metro north-south corridor, that is from CCS airport to the Municipalia, has been further considered for analysis. Shape, size, depth, surrounding ground condition are mostly similar for this above two locations, that is Delhi Najafgarh corridor and Lucknow Metro CCS airport to the Municipalia corridor. Only the differences thing is that Lucknow lies in the seismic zone 3 and Delhi lies in the seismic zone 4. So the parametric study was initially conceptualized by comparing the bending moment and the deformation of the same underground structure situated at Delhi Najafgarh corridor, which is zone 4, and the second one is the Lucknow Municipalia airport corridor, which is the situated in zone 3. This study has been further elaborated with the help of the varying soil parameter, mostly from the ground loose to medium condition, then medium to the dense sand condition, and very dense sand condition at the different seismic zone, that is seismic zone 3, 4. So the outcome of the study has been further tabulated to develop a correlation so that we can come out with a fruitful conclusions. The following three type of ground condition has been considered during my study, that is the ground condition 1, GC1, loose to medium silty fine sand from ground level to the depth of the 15 meter below the ground. The second one is the ground condition 2, GC2, medium to dense silty fine sand, that is starting from 3 meter below the ground to the 15 meter. And here top 3 meter is basically loose silty fine sand. The ground condition 3, very dense sand from starting from 5.5 meter below the GL to the 15 meter below the GL. So here top 5.5 meter is basically loose to medium silty fine sand. So in the table you can see the different type of geotechnical parameters for different type of ground condition. So this parameter has been used for my analysis. Soil structure interaction has been considered by assigning linear spring with the stiffness based modulus of the subgrade reaction as per IS 2950. During soil investigation, actual water table was found at 18 meter below the ground. However, during the tunnel excavation, we could not found any water table. So cohesion of the Delhi and the Lucknow silt was initially taken as a 0, as a cohesionless silt. Vertical surcharge and the lateral earth pressure has been calculated based on the adopted soil parameter for different ground condition, and the same has been applied in the numerical model to get a appropriate load and load combination and the result. Internal analysis part of the parametric study has been conducted for 6 different type of situation for 3 different ground condition, that is ground condition 1, 2, ground condition 3, and 2 different seismic condition, that is the seismic zone 3 and seismic zone 4. The different soil parameter with different seismic level causes the change in the force application and the deformation behavior of the structure. So this has been reported, this has been tabulated here, and we can see the data from our result and discussion section of this presentation. So result and discussion. First one is the comparison of the racking deformation under the different surrounding soil and the seismic condition. So racking deformation of underground box structure for 3 different ground conditions. We can see that the ground condition 1, GC1, loose to medium, then ground condition 2 and the ground condition 3. And these are the racking deformation value of a cut and cover box structure. This is for the seismic zone 3, and this value are for the seismic zone 4. We can see that the racking deformation value gradually decrease with the improvement of the soil condition. Once the soil condition improve from the loose to medium, then to medium to dense, the racking deformation value getting reduced actually. And then from the medium dense to very dense, racking deformation further is even in the same seismic zone. The same is happening for seismic zone 3, then seismic zone 4. And the interesting thing is, once the seismic zone change from zone 3 to 4, the racking deformation value increased significantly due to the change in the seismic zone, even in the same ground condition. The second one is the bending moment comparison of an underground box wall for different surrounding ground and seismic condition. So in the table you can see in the wall we have shown the.
I request you to conclude in 1 or 2 minutes, please.
Yes, sir. You can see the bending moment value at roof slab junction location, at the mid of the wall location, the base slab location for 3 different type of ground condition. In the table 1 for the non-seismic condition, middle one for seismic condition zone 3, and the bottom was the seismic condition zone 4. Each and every case you can see, sir, with the increasing of the ground condition, the bending moment value getting reduced, and also with the improvement of the seismic zone, the bending moment value increased significantly. Means once the ground condition change from loose to medium and medium to dense, then bending moment getting reduced, and once the seismic level is getting changed from 3 to 4, the bending moment getting increased. So these are the comparison curve for 3 different ground condition. The similar result we have identified for cut and cover box structure for the roof slab. It is the similar result you can see the roof slab at cut and cover box structure junction location. And the similar result, you can see the curtain cover box structure at the bottom slab. It is also the bottom slab wall junction location. You can see the bending moment getting reduced once the ground condition change from loose to medium, then medium to dense. And also bending moment getting is increased once the seismic level change from the non-seismic condition to seismic 3 and further seismic 3 to 4. It's increased significantly. So conclusions, in the current study, a series of parametric study were carried out to examine the full tunnel soil interaction. So from the present study, following conclusion can be drawn. Deformation causes by the surrounding ground condition gradually decrease with the improvement of the surrounding ground condition. So with the improvement of the ground condition from GC1 to GC2, then GC2 to GC3, the racking deformation value basically reduced by 26% and further 16% respectively. Racking deformation value increased significantly once the seismic condition changed from the lower to the higher seismic zone, that is from the zone 3 to 4. We can see that the racking deformation increased by 113% also. So with the improvement of the surrounding ground condition, the bending moment at the roof slab at wall junction location is reduced by 1 to 5%, whereas the bending moment of the roof slab is increased by 6 to 12% once the seismic level change from the zone 3 to 4. The similar result we can see from the result from the base slab. The base slab value, bending moment value of the base slab is reduced by 4 to 13% once the ground condition improve. And once the seismic level change from the 3 to 4, the bending moment of the slab further increased by 25% to the 38%. So bending moment value of the wall is gradually decreased with the improvement of the surrounding ground condition. However, the behavior of the wall is not uniform, is changed at the different location. Means with the improvement of the ground condition from with the improvement from loose to medium, then medium to dense, and then very dense, bending moment value reduced by 1 to 4% at the wall roof slab junction location. At the mid location, it is 17 to 31%, and at the base location, it is 17 to 22%. Whereas the bending moment value at wall and the slab junction location is increased by 5 to 11% once the seismic level change from the 3 to 4 seismic zone 3 to 4. And at the mid slab mid wall location, it is increasing by 5 to 13%, and at the base slab junction location, it is increased by 23 to 32%. So these are the outcome of my study. So hope that this result will be helpful for practicing engineer during the design of the curtain cover box tunnel for metros or subways. Thank you, sir. These are the.
Yeah, thank you for your nice presentation. So no question from the audience, but I have one small question. So how did you consider any damping of the soil in your analysis?
Yes, sir. Consider the damping of the soil.
Okay. How much percentage damping you have considered?
Actually, it's 0.5, sir.
0.5. Okay. Okay. Yeah, I think thank you for your nice presentation then. So I invite the next speaker, Athira VS of BITS Pilani, to present paper on seismic analysis of buildings in hilly areas with and without base isolation and cable support system. So Athira, are you here?
Yes,
yeah.
sir. Yes.
Okay.
Thank you.
So you can share your screen.
Okay. So hi, I'm Adira. My topic for today's presentation is seismic analysis of buildings in hilly areas with and without base isolation and cable support system. So we know the challenges we face when we are constructing a building in basically a hilly area. So the challenges are more when these buildings are located in earthquake prone areas. So because the foundations will be at different levels in a hilly area, and also the column heights in the same story will be different. That is, there will be short columns as well as long columns in the same building, and hence the building will be irregular in both horizontal as well as in vertical directions. So because of this unequal column heights, that is, there will be short columns as well as long columns. The short columns attract more forces, earthquake forces, as the short columns are more stiffer. And all these are the major challenges faced when we are constructing a building in a hilly area. Now, these are the few configurations of buildings in hilly area: step back building, step back setback building, and steep slope building. And in India, few vernacular practices are followed, that is Gaji wall, Katkuni style and Tatara style in hilly areas. And even though these are very good in resisting earthquake, the major problem lies in its raw materials. That is, the major raw material is timber, which is not at all a durable material. That is, it is much prone to termite attack and water attack, and hence the durability of these structures are reduced. So, considering all these difficulties, we thought of doing these as keeping these as our objectives. That is to study the behavior of buildings in hilly areas during an earthquake, and we provided base isolation to the same building and analyzed, and then we provided cable supports to the building and analyzed it with the and compared the results with without any protection systems. And we know base isolation is nothing but separation between the foundation and the superstructure using some elastic systems, and it enables the reduction in earthquake forces by increasing the time period of the structure. And cable supports are very uncommon in India, and these are very few structures which are around the world. And our methodology we followed is that we modeled a 5-storied building in a hilly area, and we subjected it to a seismic loading, and then we provided base isolation to the same building and analyzed, and then we provided cable supports and analyzed, and then we came up with another method where we introduced cable supports as well as base isolator to the same building, and all these results were compared. So I'll just brief on our 4 models. That is, first, model A is fixed base building without any protection. Model B is base isolated building. C is building with a cable support, and D with the combination of cable support and base isolation. So this is our plan of the building, and this is how it looked. Our elevation, we modeled it in ETABS. So these are our building details. We modeled an RCC building, and this is the base isolated structure, and this is the cable structure, and we adopted steel rods of 100 mm diameter for the building. So we designed the base isolator according to UBC 97 code, and since the foundation is at different levels, the reaction it was facing in all the levels were different. So we designed base isolator in different levels. So that is what is shown here. And base isolator, for that is, in the structure we provided cable supports, and we found that the maximum reaction faced by each level was less when compared to the base isolated structure. So the reduction in the reaction actually reduced the horizontal and vertical stiffness required for the base isolator. So this can actually reduce the cost of the base isolator. Base isolators are very uncommon in India because of its expenses. So here, when we introduced cable supports, it acted as a stiffener, which actually decreased the stiffness required for the isolators. So from the 4 models designed, these are results we got. And variation of time period, obviously the introduction of base isolators increased the time period of the structure. And the model B is the base isolated structure. It had the highest time period, and it reduced to some extent for the cable plus base isolated structure, whereas the cable structure and the fixed base structure behaved similarly. Maximum story displacement also, it was observed higher for the base isolated structure, which reduced to some extent for the combination structure. And story shear, we found it, we got a non-uniform pattern, and it was because we had different plan area in different floors. So then also we got higher story shear for fixed base building and cable supported building, and the story shear decreased very much for the base isolated and cable supported buildings. And story acceleration is nothing but an indicator for the force acting, that is inertia forces acting, as force is directly proportional to the acceleration. And it is very interesting to note that the model D, that is the combination of cable support and base isolators, reduce the acceleration to a great extent, and this is what we wanted. And base shear is actually also the lateral force acting at the base of the building, and this was reduced considerably for the base isolated as well as cable supported, the combination building. And since the base shear, the forces acting are less for model B and model D, the moment also reduced considerably for the same. Yeah, so from these results, we can actually conclude that the base, obviously the base isolator provided building gave the better results, but the cables can also be provided in such buildings which can act as a stiffness provider, and hence the base isolator size can be reduced to a considerable extent. And then even though less stiff base isolator with cable did not perform better than the base isolated building, it can be a choice. However, the introduction of cables did not save the building actually. So a few gaps in our studies that we can actually provide the cables all around. We provided it only on one side of the building. We can actually optimize the shape of the road, or we can actually provide it anywhere in the building, and we can compare the results. And other stiffness providers can also be provided, like instead of cables, another stiffness providers can also be given, and the results can be compared. And yes, references. Thank you.
Thank you, Atira, for nice presentation. So there are no questions. So I have one small question again. So can you please comment on the cost aspect of this, cable support to include in the base isolation system?
Okay, cable supports, actually these are only steel rods of 100 mm diameters. So I think and only the 4 or 5 are required. So I don't.
So
we have not
you
gone to the
think,
cost
yeah.
analysis.
So that means it's not adding too much into the cost, what I can get from you.
Yeah.
Okay.
Yes.
Okay. So good work. Okay.
Thank you.
So there are no more questions. Then I thank you. Okay. And with that, I think all the 3 papers have been presented, and one Dr. Ketan Bajaj is absent. So with that, I think I'll just summarize this session. So in total, we had 3 very good papers covering different aspects of seismic design of the foundation, typically on pile foundation, then underground box structures, and also the last paper which spoke about base isolation of the buildings with the novel, cable support technique. So I want to place on record that all the 3 presenters have presented excellently. All the 3 papers. And all the 4 papers gave into a deep insight into the latest research in this particular theme. So with this brief comment, now I hand over the sessions to our chair, Dr. Ravikiran Vaidya, for his concluding remarks and also for closing the session. Over to you, sir.
Thank you, Dr. Hegde. Yeah, it was a very nice session with a variety of papers, and they were all well presented. We are very much within the time limits. I think there's not much discussion. There was one more question for Professor Ayothiraman. So I'm not sure if he is still logged in. If not, I think maybe the organizers can forward this question to him for any further replies.
Sir, I am there, sir. If there is what is the question, sir? I am there.
Okay. So this question is from Anand Dude. And what he asks is, what are the state-of-art methods for analyzing the rectangular tunnels constructed using cut, construct, cover method in weather drop conditions for seismic impact loading? You can see the question number 4 below the question of Mr. Mohan Ramanathan.
Sir, question number 4, no? Yeah. Okay. Yeah, I think we apply the displacement methods, the displacement obtained from the free field, we superimpose them. So there is a guideline by Eurocode also, how to apply the displacement for a racking analysis. Actually, we can do that for cut and cover and the rectangular tunnels.
Okay, so
yeah.
I hope the answer is conveyed. I also take the opportunity to thank the organizers for allowing me to chair this session. With this, I hand over the session to the organizer, Dr. Srivalsa, to take over and declare the session officially as closed.
Thank you very much, Ravikiran Vaidya sir. So on behalf of the organizing committee, I place my sincere thanks to Mr. Ravikiran Vaidya sir for chairing the session and to Dr. Amarnath Hegde for co-chairing the session. So you have very efficiently handled the session. So we are on time and we had enough time for discussion as well. So thanks to Professor Ayothiraman for delivering a wonderful talk and to all the presenters. So we place our sincere thanks. So once again, thanks to Mr. Ravikiran Vaidya and Dr. Amarnath Hegde for conducting this session very efficiently. So we formally close the session here and I invite all of you to join session of your interest from 2 p.m. onwards. So there will be similar parallel technical sessions going on from hall A to D. So you can join any session of your interest. After that, there will be a plenary talk as well in the evening. So please explore and enjoy the conference. Thank you. Thank you very much. Thank you all.
Thank you. Thank you.
Thank you.
Dr. Shival,
Thank you,
sir.
Dr. Shival, sir.
Great to
Thank you.
be there.
Thank you.
Bye-bye.
Bye.
See you all. Thank you.
Bye. Bye, sir. Thank you.
Bye-bye.
Bye.
Thank you.